I want you to start by doing something for me.
It requires a little bit of trust, but I promise it's worth it.
Just for a moment, I want you to close your eyes. If you're driving, obviously keep them open, but maybe just let your mind wander a little bit from the road. If you're at home or on the train or sitting at your desk, just let the eyelids get heavy for a second.
Go on.
Forget the room you're sitting in. Forget the notifications piling up on your phone.
Forget the noise of the day, the hum of the refrigerator, the distant sound of traffic. Just let it all drop away.
Take a deep breath.
Hold it for a second and let it out.
Now, I want you to imagine that you are floating.
You're completely weightless.
You have left the Earth behind. You have left the solar system behind. You are drifting in the absolute crushing silence of deep space.
And it's not just quiet here. It's a profound, ancient silence. It is a vacuum.
Right. There's no air to carry sound, no wind.
There's just you, suspended in the void.
It creates a very specific sensation, that kind of darkness.
Oh, it does. We tend to think of space as, empty, as just a lack of things. But when you are out here, thousands of light years from home, the darkness feels
Heavy.
heavy. That's a good word for it.
It feels like velvet. It wraps around you, and it stretches on for eternity in every single direction.
And if you look around trying to find a landmark, trying to find home, you can't.
You're lost.
You are 3,000 light years away from Earth. Our sun, our massive, life-giving star, is just another pinprick of light out here. It is lost in a sea of diamonds, indistinguishable from the billions of other stars scattered across the Milky Way.
You are entirely alone in the theater of the cosmos.
But as your eyes adjust to this heavy darkness, as you drift through the constellation of Cygnus, the Swan, you realize that the void isn't actually empty.
There is something there.
A shape is emerging from the gloom.
It's faint at first. It's not a sharp point of light like a star.
It's not a solid disk like a planet. As you drift closer, the shape becomes clearer. It's glowing.
Ethereal. Almost ghostly against the black backdrop. It looks, well, to be perfectly honest, it looks like an egg.
A glowing cosmic egg, shrouded in these concentric shells of dust, just shimmering in the vacuum.
It is one of the most mysterious, one of the most visually stunning, and frankly, one of the most confusing objects the universe has to offer.
Astronomers call it the Egg Nebula.
But what you are visualizing right now isn't just a static object. It's not a rock floating in space.
No, it is a cosmic moment.
A moment frozen in time. I like that. That's a beautiful way to put it.
Exactly. It's a fleeting snapshot of a star's final, violent, and yet strangely beautiful transformation.
You are looking at a funeral pyre that is burning across the light years.
You are looking at the death of a star caught in the very act of dying.
And the reason we are floating out here today, the reason we are taking this deep dive into the void of Cygnus, is because of a brand new image that has just dropped.
A really spectacular one.
As of February 10th, 2026, NASA and the European Space Agency released a capture that has the astronomy world absolutely buzzing. They're calling it a light show around a rapidly dying star.
And we have the privilege today of unpacking exactly what this image means and why it matters to us down here on Earth.
And light show it's barely doing it justice.
You think so?
I do. It sounds like fireworks, which are temporary and surface level. But when we look at this image of the Egg Nebula, we aren't just looking at pretty colors in the sky. We are looking at high-energy physics in action. We're looking at the mechanics of matter creation.
And in a very real, very literal sense.
So you're looking at our own future.
That's the hook right there.
Yeah.
Our own future. It sounds ominous, but also compelling.
It's both.
We're going to get to that, the existential dread and the hope, but let's start with the discovery itself. This image, it's hitting the news feeds right now. NASA, ESA, Space.com, everyone is talking about it.
It's the picture of the week for sure.
The headline is essentially, Hubble captures light show around rapidly dying star. But before we analyze the star, let's talk about the photographer, the Hubble Space Telescope. We are in 2026. Hubble launched in, what, 1990?
1990. That is 36 years ago. That is ancient in technology terms. I mean, think about the computer you were using in 1990 if you were even alive then.
I had one. It barely had a hard drive. You booted it from a floppy disk.
Exactly. And yet, here is Hubble, this relic, still making headlines.
It's incredible, really. It's a testament to the engineering. In an era where our phones become obsolete in 18 months, Hubble is still up there, acting as our sentinel. It is an aging eye, but a resilient one.
It's interesting because we have the James Webb Space Telescope, the JWST, which has been the superstar for the last few years, hasn't it?
Oh, absolutely. Everyone is obsessed with Webb because it sees in infrared and it's massive.
But Hubble sees invisible light, and that distinction matters here, doesn't it?
It matters immensely. Hubble sees the universe the way our eyes would see it if our eyes were, the size of a school bus and we were floating above the atmosphere.
Yeah.
And for the Egg Nebula, that visible light perspective is crucial.
So why is that? Why couldn't the James Webb just take his picture and make it look even sharper? I mean, isn't it the more powerful telescope?
It is more powerful in certain ways, but it's designed for a different job. It's all about the dust.
Yeah.
And we are going to be talking a lot about dust today.
Okay.
See, the James Webb Telescope is designed to be a heat seeker. It looks into the infrared spectrum. Infrared light is very long wavelength light, and it has this special property. It cuts through dust like it's not even there.
So it ignores it.
It ignores it. If Webb looks at the Egg Nebula, it looks right through the beautiful shells we are describing and sees the hot thermal signature inside. It sees the body under the clothes, so to speak.
But in this case, we want to see the clothes. We want to see the costume.
Exactly. We want to see the texture. Hubble allows us to see the light scattering off the dust, bouncing off the surface. It captures the fog, the way the light plays off these ancient particles. If you want to see the sculpture of the cloud itself, you need visible light. You need Hubble.
So looking at the source material, this release from ES and NASA, it describes the image as a dramatic interplay of light and shadow. I'm looking at the high-resolution file right now, and dramatic feels like an understatement. It looks like a lighthouse in a storm.
That is a perfect analogy,
Yeah.
a lighthouse in a storm.
Yeah.
Because what we are seeing is not a steady, calm glow.
No.
It is a dynamic, shifting environment. This image is a freeze frame of an explosion in slow motion. We are witnessing a star that is literally tearing itself apart, shedding its skin. But because of the vast distances and the timescales involved, to us, it looks like a serene, glowing egg.
Let's try to paint the picture for the listener who can't see the screen right now.
Let's do it.
We've set the scene. We're in the dark looking at this object in Cygnus, but let's get into the anatomy of the egg. If you're listening to this, I want you to try and visualize this structure in your mind's eye. We aren't seeing a round ball of fire like the sun.
No, definitely not. Imagine a pitch-black room, total darkness. In the center of the room, you have an incredibly bright lantern, a light source of immense power. But that lantern has been covered up by a thick, heavy, dark velvet cloth.
Okay.
You can't see the bulb at all. The source is completely obscured.
I'm with you. The light is trapped inside.
Right. It's suffocating in there. But imagine someone has poked holes in the top and the bottom of that cloth, like at the north and south poles of the lantern.
So the light has an escape route. It's channeled.
Exactly. So what you get are these twin beams of light, searchlight beams, shooting out vertically into the darkness. In the Hubble image, that is exactly what you see. You see these two distinct, sharp cones of light piercing through the gloom.
And they're glowing with this pearlescent golden hue. It's incredibly stark against the black background. It looks artificial. Honestly, when I first saw it, I thought that looks constructed. It's so symmetrical. It doesn't look like the random chaos I expect from a cosmic explosion. It looks engineered.
And that's a common reaction. Nature loves symmetry, but here, physics dictates it. Those beams are the result of the star's light finding the path of least resistance.
How so?
The star is surrounded by this thick donut of dust. Astronomers call it a torus that blocks the light from the equator. Imagine a ring around the star that is so thick, so dense, that light cannot get through.
Like an inner tube of dust.
A perfect way to put it. So the light has nowhere to go but up and down. And as it shoots out into the void, it acts like a flashlight in a foggy room. It illuminates the gas and dust that the star has previously puffed out.
And that leads us to the egg part of the name. Surrounding these beams, there are these arcs. They look like ripples in a pond or layers of an onion.
Precisely. These are the concentric shells. And this is where the detective work of astronomy really shines. When we look at those shells, we aren't just seeing decoration, we are reading a history book.
A history book.
Each ring, each shell, represents a distinct episode in the past where the star convulsed.
Convulsed, like a heartbeat or a hiccup.
More like a seizure or a violent cough. A very violent, very slow cosmic cough. The star expands, cools down, sheds a layer of its outer atmosphere into space, then it contracts and heats up again.
Wow.
Then, a few hundred years later, it repeats the process. These shells are the echoes of those convulsions, ripples traveling outward.
And in the Hubble image, they are glowing faintly fading out into the deep black of space.
You have the bright, sharp beams in the center and then these softer, ghostly rings rippling outwards, telling the story of the star's instability.
And the colors, we mentioned gold and pearlescent, but I'm also seeing these dark stripes cutting across the light. What's that about?
That is a study in chiaroscuro, the interplay of light and dark. The light is this warm, yellowish white reflecting off the carbon dust, but then you have these sharp, dark bands cutting across the beams.
They look like the rungs of a ladder climbing into the darkness.
Yes, that's exactly what it looks like. A ladder of light.
So what are they?
Those rungs are actually shadows.
Shadow.
Shadows. This is what blows my mind. We are seeing shadows cast across light years.
I can't even process that.
There are thicker clumps of dust closer to the star blobs of material that are opaque. They are blocking the light. So you have the beam, and then a shadow cast by a dust clot, and the beam again. It projects these long shadows billions of miles out into space.
The scale of this is just, it breaks my brain a little bit. We're talking about beams of light and shadows. How big are we talking? When I look at those beams, can I imagine them relative to Earth?
Oh, they dwarf everything we know.
Yeah.
The structure we are seeing spans a significant portion of a light year.
A light year, which is about 6 trillion miles.
Around that, yeah. So to put that in perspective, think about the Voyager probes. They launched in the 1970s. They are humanity's farthest ambassadors. They've been traveling at tens of thousands of miles per hour for nearly 50 years.
And they're barely outside our solar system, right?
Exactly. They're just now considered to be in interstellar space. If you superimposed our entire solar system onto the Egg Nebula, the entire orbit of Pluto, everything we consider home, every planet, every asteroid would be a microscopic dot in the center of that glow.
So these beams of light are trillions of miles long.
Trillions, easily.
Yeah.
We're looking at something titanic.
And yet looking at it, it feels so delicate. The egg. It sounds fragile. It looks soft.
It is fragile in a temporal sense. It's a transient structure that won't last long. But physically, it is a maelstrom.
A maelstrom.
Winds are blowing there at hundreds of kilometers per second. It is a violent, chaotic environment masquerading as a still life painting.
Okay, I want to dig into the center of this thing. We talk about the beams, the shells, the shadows, but what is making all of this happen? We keep saying the star, but looking at the picture, you can't actually see a star, can you?
That is the great irony of the Egg Nebula. The star itself, the engine driving this entire show, the source of all that energy, is invisible. It is completely hidden from our view.
Hidden by what? Just the dust.
By its own creation. The star has ejected so much material, so much dust and gas, that it has effectively buried itself in a cocoon.
So it built its own tomb.
Or its own chrysalis. The dust is so thick that visible light cannot punch through it. That dark band running through the center of the nebula, separating the two beams, that is the cocoon. The star is buried deep inside that knot of darkness.
So the light we are seeing, then it's not coming from the nebula.
It is, but it's all reflected light. We are seeing the starlight bouncing off the dust particles further out. It's like seeing a flashlight beam cutting through fog. But the person holding the flashlight is hidden behind a wall.
Okay, that makes sense.
You know the source is there because of the effect it has on the environment, but the source itself is veiled.
So what kind of star is it? Or was it? Because if it's dying, is it still a star?
It is, for now. It was a star very much like our own sun, a main sequence star. For billions of years, it was a stable, happy fusion reactor, fusing hydrogen into helium, shining steadily.
Just like our sun is doing right now.
Just like our sun. But eventually, like all things in the universe, it ran out of fuel in its core.
And that's when the trouble starts.
That's when the transformation begins. When a star like this runs out of hydrogen in its core, the delicate balance between gravity pulling in and energy pushing out is broken. The core collapses, and the outer layers, they expand dramatically.
It becomes a red giant.
It becomes a red giant. It swells up to an enormous size. If this star had planets, it likely swallowed the inner ones. It becomes cool and red and pulses. And that pulsating red giant phase is what created those shells we see.
So the star is basically dying. It's in its death throes.
It is. But death for a star isn't an instant event. It's a process. And right now, this star has passed the red giant phase. It has shed those outer layers. Now the core is shrinking and heating up.
Then what's it becoming?
It is transitioning from a red giant to a white dwarf. And the Egg Nebula is the snapshot of that transition.
Okay, this leads us to the technical term for this, which I found in the notes. Protoplanetary nebula.
That's the one.
Now, I have to stop you there because when I hear protoplanetary, I think baby planets. I think about a solar system being born. But we just said this star is dying. So Who messed up the naming convention? Because that is confusing.
Laughs. You can blame the astronomers of the 18th century for that one.
Okay.
Specifically William Herschel, the guy who discovered Uranus. You have to remember, back then, telescopes were pretty terrible compared to what we have now. They were polished bronze mirrors and small lenses.
Right, they didn't have Hubble, they saw blurry dots.
Exactly. When early astronomers looked at these objects, they didn't see the complex structures Hubble sees. They didn't see the beams or the shells or the shadows. They just saw small, round, greenish blobs.
And they thought they looked like planets.
They looked a bit like planets, specifically Uranus or Neptune, which are gas giants, so they called them planetary nebulae.
So it has absolutely nothing to do with planets.
Nothing at all. It is purely a visual similarity to the stuff. It's a misnomer. A planetary nebula is actually the death shroud of a star. And a protoplanetary nebula, which is what the egg is the phase just before the true planetary nebula phase.
Okay, so protoplanetary in this context means pre-planetary nebula, not pre-planet.
Exactly. It's confusing, I know. But think of it this way. The egg nebula is the caterpillar inside the cocoon.
Okay.
It has spun the silk, those dust shells we see. It has hidden itself away, and it is changing. It isn't quite the butterfly yet.
What is the butterfly in this analogy? What's the next stage?
The butterfly is the true planetary nebula phase. That happens when the central star gets hot enough, really hot, like 30,000 degrees Celsius, to blast out ultraviolet radiation.
Okay, so it gets much, much hotter.
Much hotter. And that UV radiation will hit the surrounding gas and make it glow on its own. It will ionize the gas. Then the nebula will light up like a neon sign. Bright greens, reds, blues. That is the butterfly stage.
Yeah.
The ring nebula or the dumbbell nebula, those are famous examples.
But right now, the egg isn't glowing on its own, it's just reflecting.
No, not yet. Right now it's just reflecting. The star isn't hot enough yet to ionize the gas. It's just a spotlight in the dust. And that's why this phase is so rare. We are catching the star in that brief window between shedding its skin and lighting up the gas.
How brief is brief in cosmic terms?
A blink of an eye.
Yeah.
We are talking maybe a few thousand years.
A few thousand years, that's it, for the whole phase.
That's it. In the life of a star that lives for 10 billion years, a few thousand years is nothing. It's a millisecond.
It's like
walking into a room and catching a glass falling off a table before it hits the floor. That is why the egg nebula is so special. We don't see many of these because they don't last. By the time we look, usually the star has already moved on to the next phase. Catching one in this specific egg configuration is incredibly lucky.
That makes the image even more poignant. We're looking at something that, astronomically speaking, is vanishing right in front of us. If we came back in 10,000 years, this beautiful egg might be gone, replaced by a ring of neon gas.
Almost certainly. And the physics happening inside that vanishing moment are fascinating. We talked about the dust earlier. Let's dig into that because the Light Show headline from NASA is really a story about dust.
Okay, let's talk dust, because when I think of dust, I think of the stuff under my couch, or maybe the stuff I wipe off my bookshelf. I assume cosmic dust is a bit more exotic.
A little bit, but not as much as you'd think. This dust is carbon-rich. The source material mentions freshly ejected stardust. This is soot, essentially.
Soot, like from a fire.
Exactly. Tiny particles of carbon and hydrocarbons.
So the star is basically smoking, like a broken engine.
It is billowing smoke. And these particles are incredibly small microns in size. But they are the perfect size to interact with light. This brings us to a bit of physics called scattering.
Don't lose me here. Keep it simple.
I'll try. Think about a movie theater. If the air in the theater is perfectly clean, you don't see the beam of light coming from the projector.
Right, you just see the movie on the screen.
You only see the movie. The space between the projector and the screen is invisible. But if there's a bit of smoke or dust in the air,
you see the beam. You see the cone of light cutting through the room.
Exactly. The dust particles scatter the light sideways into your eyes. That is precisely what is happening in the Egg Nebula. We are seeing the projector beam of a central star because the room, the nebula, is filled with this carbon dust.
And the light bounces off it?
The light bounces off the particles, Rayleigh scattering and Mies scattering if you want the technical terms, and comes back to Hubble.
Mies scattering? That sounds like a name.
Gustav Mies, a German physicist. He figured out how light interacts with spheres that are about the same size as the wavelength of the light.
What does that mean in this context?
It explains why clouds are white, actually. The water droplets in a cloud are just the right size to scatter all the colors of sunlight equally, which our eyes see as white. Here, The carbon dust is a specific size that preferentially scatters certain wavelengths.
And that explains the color of the nebula, too, that golden white color.
It does. The size of the grain determines how it scatters different wavelengths of light. This dust is creating that polarization, that pearlescent glow we see in the image. It's also creating the shadows.
Right, the ladder rungs.
The clumps of dust that are too thick for light to pass through act like the silhouette of a hand in front of the projector. They cast those long, dark shadows that look like the ladder rungs.
It's amazing to think that simple dust and geometry can create something that looks so complex. It feels like art.
It is physics as art. But there is a bigger picture here. We aren't just looking at a pretty object in Cygnus. We are looking at a mirror.
A mirror, what do you mean?
A mirror of our own destiny.
Okay, let's go there. Because you mentioned earlier that this star was like our sun.
Yes. The star inside the Egg Nebula started its life with roughly the same mass as our sun. It lived a life very similar to our sun, which means essentially we're watching a preview of the sun's death.
That's sobering. I know we have a long time, but still, it makes you pause.
We do have time. In about 5 billion years, our sun will run out of hydrogen fuel in its core. It will destabilize, it will swell up into a red giant.
And expand out.
It will extend out past the orbit of Mercury, past Venus.
Will it hit Earth?
It's debated. It might swallow Earth, or it might just roast it to a cinder as it gets incredibly close.
Yeah.
But either way, the inner solar system is gone. The atmosphere, the oceans, life, long gone.
Right.
But then the sun will begin to pulse, just like the star in the egg. It will shudder. It will cough out its outer layers. It will eject its atmosphere into deep space.
Creating its own shell, its own cocoon.
Exactly. For a brief moment, a few thousand years, our solar system will look like the Egg Nebula to some distant observer.
That's a wild thought.
We will have twin beams of light shooting out from the dying sun. We will have concentric shells of gas expanding into the void. And then the sun will shed its skin completely. The core will become a white dwarf, and the gas will light up into a planetary nebula.
It's a beautiful way to go, I guess. Better than just vanishing. Or exploding and taking out the whole neighborhood like a supernova.
That's the thing. Our sun isn't big enough to go supernova.
Right.
It doesn't have the mass. It will go gently. It is a glorious finale. But here's where it gets really interesting. This isn't just about death. It's about recycling.
Cosmic recycling. I love this concept.
Think about what that dust is. We said it was carbon-rich. Hydrocarbons, where did that carbon come from?
It came from the star, right? Through fusion.
Right. But the star started as mostly hydrogen and helium. The carbon wasn't there at the beginning. The star manufactured it. For billions of years, through nuclear fusion, deep in its core under immense pressure and heat, it smashed atoms together to create heavier elements.
Carbon, nitrogen, oxygen.
The stuff of life.
So for billions of years, the star is a factory. It's working away.
It's an alchemist. It turns simple gas into complex elements. But as long as those elements are locked in the core of the star, they're useless to the universe. They are trapped in the furnace.
Until the star dies.
Until the star dies. This violent process, this coughing out of the layers, is the delivery mechanism. The Egg Nebula is basically a cosmic crop duster. It is spraying these heavy elements, this carbon, this oxygen, out into the galaxy. It is enriching the interstellar medium.
The interstellar medium, that's the space between stars.
Yes. And that space isn't empty. It's filled with giant cold gas clouds. And when this soot from the Egg Nebula mixes with those clouds, it seeds them. It provides the building blocks for the next generation of stars. And not just stars.
Planets.
And people.
That's the famous Carl Sagan quote, right? We are made of star stuff.
It's not just a poetic quote. It is literal scientific fact. The carbon in your DNA, the oxygen you breathe into your lungs, the nitrogen in your muscles, every single atom of it, other than the hydrogen from the Big Bang, was forged in the belly of a star that died billions of years ago.
A star that went through a phase exactly like the Egg Nebula.
Exactly like this.
So when we look at this image from Hubble, we're looking at our ancestors, in a way, or at least the process that made us possible.
We are looking at the origin story of matter itself. Without these dying stars, the universe would just be boring hydrogen and helium. There would be no chemistry, no biology, no life. The death of this star in Cygnus is the planting of seeds for future worlds that won't exist for millions of years.
That recontextualizes the whole thing. It's not a funeral pyre. It's a dispersal, a sowing of seeds.
Exactly. It's a cycle. The end of one thing is the absolute prerequisite for the beginning of another. The universe wastes nothing.
I want to pivot back to the tool that gave us this perspective, Hubble. We mentioned it briefly at the start, but I think it deserves a bit more love. This telescope is a legend.
It is the most important scientific instrument ever built, arguably. It changed the way we see the universe, literally and figuratively.
And it's still working. I mean, looking at the sources, we have all this news about the Ariane 6 launcher, the SpaceX Crew 12 mission, the new Roman Space Telescope. Space is getting crowded with new tech, but Hubble is still there, holding its own.
It speaks to the engineering, but also to the foresight of servicing it. Astronauts went up there 5 times to fix it, upgrade it, replace the batteries and the gyros.
Right, they gave it corrective lenses in the beginning.
They did. That's why we can get images like this in 2026. But what's fascinating is how Hubble fits into the modern ecosystem of telescopes.
Right, because we have the James Webb now, and the Roman telescope is coming online. Do we still need Hubble, or is it just sentimental at this point?
We absolutely need it. It's not sentimental at all. Astronomy today is multi-messenger or multi-wavelength. You need to look at an object in as many different kinds of light as possible to get the full picture.
Okay.
As we discussed, Webb sees heat. It sees infrared. If Webb looked at the Egg Nebula and it sees the glow of the warm dust and it can peer through to see the hidden star, that gives us data on the temperature, the mass, the core dynamics.
But it doesn't give us the picture in the same way.
It doesn't show us the scattering. It doesn't show us the shadows in the same way. To understand the structure of the nebula, the geometry of the shells, the density of the dust, you need to see how visible light interacts with it. You need Hubble. They are a team.
So one gives you the skeleton.
And the other gives you the skin. We need both to understand the organism.
And looking at the history of how we understand these objects, before Hubble, what did we think these were? You said blurry blobs, but was that really it?
Before Hubble, planetary nebulae were mostly just fuzzy blobs. We knew they were gas, we knew they were dying stars from their spectra, but we had no idea how complex they were. We assumed they were just expanding spheres.
Simple, round, boring.
Like a balloon blowing up evenly in all directions. That was the leading theory.
Right. But then Hubble opened its eye in the 90s and looked at the Cat's Eye Nebula, the Ring Nebula, the Egg Nebula.
And suddenly we saw structure. We saw symmetry. We saw wings and hourglasses and spirograph patterns. It revolutionized our understanding of stellar dynamics. We realized that stars don't just explode or puff out evenly. They are sculpted.
Sculpted by what?
By unseen forces. That's the big question. It could be powerful magnetic fields channeling the gas like a railgun. It could be the star's own rotation flinging material out from its equator. Or, and this is the big one, it could be a binary companion.
A second star.
A second star hidden in there. A binary partner that is stirring the pot, creating these waves and beams as they orbit each other. The fact that the Egg Nebula have these twin beams in this perfect symmetry strongly suggests that something is shaping the outflow. It's not random.
A hidden partner. That adds another layer of intrigue.
It often does in astronomy. When you see something this complex, this symmetrical, usually 2 stars are involved in a gravitational dance. But with the dust being so thick, it's hard to be sure. That's a mystery for future observations, maybe with even more advanced telescopes.
I love that. Even with the best eyes in the universe, there are still mysteries hiding in plain sight.
That is the fuel of science. If we knew everything, we'd stop looking.
So we've looked at the beams, the shells, the hidden star, the dust, the future of our sun, and the legacy of Hubble. I want to zoom back out, way out.
Back to the void.
Back to the void. I want you to take us back to that visualization. We are floating there, watching this silent explosion.
Imagine standing there. The silence is profound. But if you could hear the physics, if you could hear the radiation pressure, the stellar winds colliding with the interstellar gas, it would be a roar.
A scream of energy.
An unbelievable scream of energy.
But to us, it's silent. It's just light.
Light traveling at 300,000 kilometers per second. And remember, it took 3,000 years for that light to reach us. When we look at that image, we are looking into the past.
We're seeing it as it was 3 millennia ago.
That star might already be a white dwarf by now. The beams might have faded. We are seeing a ghost.
A ghost that is carrying the seeds of life.
A benevolent ghost.
You know, it makes you feel small. But in a good way, not an insignificant way.
It should. It connects us. We spend our lives worrying about deadlines and traffic and emails. But above our heads, constantly, this grand cosmic drama is playing out.
Right.
Stars are dying. Nebulae are forming. The universe is recycling itself. We are part of a much, much larger system.
And images like this, the space egg, they are a window into that system. They remind us to look up.
They do. They remind us that beauty and violence are often two sides of the same coin in nature, and that even in the deepest darkness, there is light, there is structure, there is meaning.
And there is a future being born from the past. I think that's a perfect place to leave it.
It feels right.
We're going to let you drift back into the starfield now. Let the image of the Egg Nebula fade into the distance. Watch the beams retract, the concentric shells blur into the darkness.
Until there is just the silence again.
The deep, resonant silence of the cosmos, waiting for the next light to turn on. Thanks for taking the dive with us.
Keep looking up.